But we'll move along to our next plenary speaker in this session, Ed McFowland from University of Minnesota. Take it away, Ed.
Okay, let me share my screen here. There, share. Okay, can you guys see my slides and see me? Perfect. All right, well then I will get started, and thank everyone for coming. Hope everyone is doing well. I'm gonna get straight to the point because I don't have a lot of time. And so my goal today is to make sure and make you see the value of using anomaly detection as a useful paradigm for making many of the problems that we care about across science more practical. To do so, I'm gonna start with something that is core to this conference, and that is causal inference. Okay, so let's start by defining what we mean when I say the word anomaly detection. So when I say that, like, what do you think about? What comes to mind for you? Often what comes to mind is something like fraud or hacking or spam. Often we associate anomaly detection with finding things that are unwanted or that are bad or somehow undesirable. Now, some of you may think about it a little bit differently, because if you work for a digital platform or work with them or e-commerce sites, you may be more interested in detecting spikes in customer engagement or customer purchases. But these are all just specific popular instances of a much more general anomaly detection paradigm. And so which I would define as this: identifying when a system deviates away from its expected behavior. And to be very clear, this system can be a physical one, like the sensor readings on an engine, on an airplane at like some regular interval, or a behavioral system like the purchasing behavior of customers on a website. But the key framing for this paradigm is forming some expectation of what we should see and then detecting systematic deviations from that behavior. So the question is, how does this kind of more general detection paradigm relate to causal inference? And I'm going to illustrate this using the cleanest strategy that we have for causal inference, which is the randomized experiment. And I'm going to specifically focus to start off with on the challenge of discovering treatment effect heterogeneity. Okay, so let's start by revisiting the setup of the randomized experiment. Typically, we care about understanding the effects of a treatment. Let's say we're interested in the effect of classroom size on educational outcomes. So therefore, we take our students, we randomly assign them to control, let's say regular size classrooms, and then to treatment, let's say small class size classrooms. And we get a treatment effect by taking the averages of both these groups and subtracting them. But realize that our population is made up of, lower level subpopulations. And these subpopulations may not have a homogeneous response to the actual treatment. You can imagine a situation where subpopulation levels effects kind of cancel out on average. Their true effect actually is masked by a lot of kind of null effects. Or even the overall effects can really be driven by a smaller subpopulation. And so what this means is that heterogeneity can definitely happen. And in some cases, it can be extremely important. And so if that's the case, the next question is, how can we use an idea like anomaly detection to identify which subpopulations in our experiments are actually very significantly affected? And so let's start by thinking about how we define a treatment effect. And I'm going to say that basically it is a treatment that produces different outcome distributions in the treatment group and the control group, kind of like I have on the image here. And I'm going to argue for you that an effect generates a pattern of anomalous outcomes in the treatment group. Okay, so why is that the case? Because the control group data provides the counterfactual outcome distribution for the treatment group, which means that it provides us the necessary expectation of what we should see from the treatment group if the treatment has no effect at all. So when a treatment affects at least some subpopulation, its treatment outcome distribution will have a pattern of anomalous outcomes as compared to its expectation, which we get from the subpopulation in the control group. So intuitively, if we define some tail of the distribution, like I have a vertical line here, right? Then what will happen is when we compare the treatment group to that control group, the affected subpopulation's treatment outcomes will systematically be anomalous or systematically fall in the tail of the control distribution's outcomes. So if you buy all that, then the next question is, well, how can we leverage or even build new algorithms that detect such subpopulations that are anomalous? And I'm going to tell you that we have a solution for that, at least one, and it's called treatment effect subset scan. And I don't have the time, obviously, to go through all the details of it, but I do want to provide you a little intuition. And so I gave us this very small 2-feature data set. We have just 2 features, which is ethnicity and gender. It's represented by this kind of 2-mode tensor. And you can see that each mode component is a feature value, right? And also in each cell of our tensor is a set of outcomes for all the subjects that fall into that cell. So the first thing that TESS would do with a data set like this is compute the statistical anomalousness of each treatment subject in each of these cells. And it's going to do this by turning the original outcomes that we have into p-values, which really measure how unexpected the outcome is. And then the next thing TESS will do is scan over the kind of rectangular subpopulations in this experiment to find the one that is collectively the most anomalous. And for example, we have detected here Black or Hispanic females as being this anomalous subpopulation. And that means that it has treatment subjects with significant p-values in it, okay? So hopefully that kind of makes sense as a framework of thinking about it. And so the next thing we're gonna do then is actually talk about how do we compute these p-values to start off with. And we go to the control group, and for each cell, we compute the outcome distribution from the control subjects. So you can literally go cell by cell and get the empirical distribution if you wanted to, or you can learn some sort of more general model which combines information across cells. Either one of those will work. But the real point is that in the end, we have an expected outcome distribution conditioned on a set of covariates. Now, the next thing we do is we look at the treatment group, and for each individual cell, so let's take, for example, Black female, right? We take a Black female from treatment and we compare her outcome to the distribution of outcomes that we just estimated for Black females in the control group, right? So we do this for all Black females and all other subjects in every other cell using the appropriate control distribution to estimate it. And what we've done is we now know how unexpected each treatment group outcome is, given how extreme or essentially how far in the tail of its control group it falls. And which this allows us to now turn what we originally had as a vector of treatment outcomes into a vector of p-values. And this transformation is extremely powerful because if there is no treatment effect at all, then all of these p-values that we have a distribution of being uniform on 0, 1. And so what does that mean like for us in terms of treatment effect scanning? Essentially, let us consider a subset of cells S. Let's say Black males and Black females. And then let's pick a significance level of interest, let's say 0.1, just for sake of argument. We can then compute for our subset how many treatment subjects are in this subpopulation. That would be, in this case, how many Black subjects do we have in our treatment group? And then we can also compute in alpha, which is how many of those subjects have significant p-values. Basically, their p-values are less than our alpha significance level. And with those two quantities, we can then compute what the expected number of significant p-values would be in this subpopulation when the treatment is not affecting them at all, right? That would be n times alpha. And so with that, both the observed amount of p-values that are significant in this subpopulation and the expected, when just by random chance what should happen, we can then begin to test how different these two quantities are and understand if there's an effect possibly affecting the subpopulation. So for example, we could use a goodness of fit statistic like higher criticism here, which is really just a wall test that compares the observed and the expected number of significant p-values in the subpopulation, maximizing overall significance levels because we don't know which alpha is going to be the place where the effect is most pronounced. And so if we detect this as a subpopulation, what that basically means is that there's evidence that this subpopulation has actually been affected by the treatment. Okay, so now we have a way to actually quantify the amount of effect in a subpopulation. The problem is we still have to search because we want to be able to find the most affected subpopulation. And that search space is exponentially large for us. And so we saw that optimization problem in the paper as well. And I don't have the time, obviously, in the talk to kind of go through the details of that, but just know that we basically build an efficient ordinal ascent approach. Essentially, so for intuition, we can fix some dimension. Let's say in our case here, we fix ethnicity to be white and Asian. And then we can efficiently optimize over all subsets of the gender dimension. Okay, and let's say we did that and we got the answer was male. Then we fix male and we optimize over all subsets of the ethnicity dimension, right? Very efficiently. And let's say the answer we got there was Black and Hispanic. And now again, we fix ethnicity of Black and Hispanic and optimize over gender. And essentially the approach, as you probably are guessing, is that we're gonna keep iterating through our dimensions, optimizing one given the others, kind of scaling up in our scoring function until we converge to the local optimum of that function. And that's gonna be the subpopulation with the most evidence of an effect because its treatment distribution is the most anomalous given its control distribution. And that's really what we're proposing to do in this approach. But a question might be like, what does all of that machinery really get us? And for that, I'm gonna talk quickly about a paper that a data set we use as a test bed, which is called the Tennessee STAR experiment, which measures the impact of classroom size on test scores. It's a 4-year experiment. It's across many students, many classrooms, many schools. And the control condition is basically a regular size classroom. One treatment condition is you add a teacher's aide to a regular size classroom. And a third treatment condition basically shrinks the classroom size to be what we call small classes. In addition to this, there are a bunch of covariates capturing information on the students, on the teachers, on the type of school there are. And really the reason why I chose this is because much of the previous literature had found that there were significant effects across the board for small classrooms. That was very clear. But there seemed to be no effects for regular sized classrooms with an aide in it. So essentially these aides were considered to be not very useful. One additional thing that we did find out later, which is relevant, you'll see, is that during the last 2 years of the experiment, they also randomly gave some teachers training sessions during the summer. And if that teacher had an aide, the aide came along with them. And this was also, though, found to not be very useful, though. So the training session was proposed to not be very useful. So we did some simulations on top of this data set as a kind of a real life example where we controlled all of the parameters, right? And we kind of showed that TESS could find subpopulations with subtle effects and in these subpopulations, things like that. That was very nice. But then we also did this on the original data, unaltered, just to do a case study. And so what we did was took the data set, gave it to TESS. The control group were the students in a regular classroom. The treatment group were the students in a regular sized classroom with an aide in it. And here's what we actually found. Basically, TESS said if we considered second and third grade only with the last 2 years, and we considered inner city and urban schools, and specifically an extremely experienced teacher, then TESS said there's evidence of an effect of having a teacher's aide in the classroom. So let's take a look at the data from third grade specifically, just to kind of show what we are seeing. And this picture you're seeing right now is the full population, which the literature basically has said, and traditional regression analysis also agrees, there's no effect. And you can kind of see there seems like there's no effect. But if we look at TESS's detected subpopulation, there appears to be a very slight mean shift and a much larger skew upwards. And that piece of information is extremely important because unlike the majority of the literature kind of before us, we're considering overall distributional changes, not just mean shifts. And though to be fair, the second grade data has a similar approach, a similar view to it, but there is a very clear mean shift in second grade as well. So third grade had to kind of skew upwards, which is a distributional change. And I know the literature has thought about heterogeneity before on this topic and on this particular data set, but it's often kind of more obvious heterogeneity on kind of individual variables. And so that's sometimes not where the information actually lies. So we really see TESS as a kind of hypothesis generation tool to shine a light where the effects may exist that otherwise may go unnoticed. And that's kind of the point. In my last remaining moments, I quickly want to just say that we are also using anomalous pattern detection in the context of quasi-experiments, right? To kind of stand out. We embed TESS into, we embed propensity score reweighting into TESS to handle observational data. We use event studies to basically do anomalous pattern detection to validate the assumptions of a difference in difference, which is very important for its identification. And we also use it to detect regression discontinuities. And I'll take just 30 seconds and just kind of talk about that last one because I think it's kind of very important and interesting to think about this. And what I'll just say is that regression discontinuities is simply when a forcing variable creates an abrupt shift in the treatment variable. And I hope, I know I went through this quickly, but I hope by now you would agree with me that that is just an anomalous pattern because the observations we have deviate from the expected continuation of the curve. And so specifically, a discontinuity creates a pattern of overestimation or negative residuals on one side of discontinuity and a pattern of underestimation or positive residuals on the other side of discontinuity. So we basically built an algorithm that can search for multivariate forcing variables that induce this kind of pattern in a data. And now we can discover discontinuities instead of having to know they already exist and where they exist. So I'll stop there and basically just say, I hope that this highlights for you that there's value in thinking about anomalous pattern detection when thinking about causal inference, because treatments really just create anomalous patterns. That's what they essentially do. And that will help us enable sort of better causal inference. So I'll stop there and I'll, thank you for your attention. I know I went through quickly, but hopefully that kind of all made sense.
Yeah, that was very, very interesting. As you know, I really like the idea of searching for these regression discontinuity designs, which I think pop up so often in digital settings where there's these rules that are assigning people to treatment. And it's great to have techniques to actually find those without having to know exactly where to look. One quick question about the TESS approach. How do you handle things where a variable starts to look more continuous, or it's at least many, many valued? Do you try to do any sort of smoothing across these bins or constrain the search to pull out adjacent bins or something like that?
That's a good question. So it's important for both the control and treatment group. So in the control group, when you have a lot of bins, that leads to sparsity, which makes estimation super hard. And so the kind of cell by cell approach is not as effective. And so in the paper, we basically argue that machine learning is very good at estimating these overall models over data and bar local information. So like, some kind of random forest-based distributional approach which will understand kind of the local space is a good idea for that. And for the scanning, what we do is we always have to deal with categorical data because we're dealing with a tensor, but we can scan over intervals as well efficiently. So we can kind of look for, these ranges in continuous data, not just sort of these bins if we needed to. Those are the ways we kind of handle both those contexts. Does that make sense?
Yeah. And I think, part of the appeal of this anyway is trying to keep a lot of the interpretability. And
exactly.
So I think it's focus on categorical is great. Cool. Well, maybe we'll get to return to some of this in the panel discussion. But we're going to go to our next plenary speaker in this morning's session, and that's Katy Milkman from Wharton. Take it away, Katy.
Thank you. I'm just going to share my screen. Thanks for having me. This has been a really wonderful session. So today I'm going to talk about a related topic. No wonder we're all in this session together. I'm going to talk about a new approach to applied behavioral science, a mega study approach. So a different, and actually that I think really lends itself well to some of the analysis techniques that Edward just talked about. So this is work with so many co-authors that if I listed their names, there would be no time to present it. But let me just say that it's Angela Duckworth at University of Pennsylvania is my key partner in crime on this, and we have a team of scientists at the Behavior Change for Good initiative who helped us design everything I'm going to describe. So the motivation for this work is that I do a lot of research where we're trying to figure out what's the best policy solution that behavioral science can bring to bear to a given challenge. And this is an area of growing interest as there's been a major rise of sort of nudge units around the world, people trying to use nudge techniques a la Thaler and Sunstein to change behavior for the better. In fact, in the last 10 years since their book Nudge was published, there are now have sprung up over 200 nudge units in governments around the world. So really a lot of people are trying to figure out how do we use behavioral science solutions to policy problems. And I think there's general consensus that the best policy advice, especially when it comes from behavioral science, where we don't have sort of a single model of human behavior where we can point to variables and say this is going to move that we should ideally be basing our wisdom on field experiments, where we know there's external validity and this is likely to work the way we hope it will in the context we care about. But running field experiments has a lot of problems. First, it requires huge fixed costs and it's slow. Second, even when we have field studies to look at effect sizes, across field studies requires making apples to oranges comparisons, right? One study's done in France, the other's in California, one's with men, one's with women, different populations, different races. And you have to worry, are these really comparable? So that's an issue when we have multiple field experiments. We also have to worry about the replication crisis because it affects field work too. A lot, failed studies often end up in the file drawer and it's not totally clear what effects are robust. So that's another challenge. And so then the question becomes, okay, if we have all these challenges, we want to do more field experiments, but it's hard to do that to inform policy, what's the solution? And that's what I want to present a method to answer that question today. So what I want to convince you is a solution is the mega study. And a mega study is something we define as a very large field experiment in which many smaller sub-experiments are run synchronously with the same dependent variable. So there's a bunch of benefits of this approach if you can pull it off. One is that it allows for comparability of results across different studies, so you can make apples to apples comparisons of effect sizes. It actually means the fixed costs of executing the study can be borne by a single central organizer, creating lower marginal costs for the individual scientist. There's a lot of setup costs for a field experiment, so this just is very efficient. It reduces the risk of learning nothing useful from your field study and eliminates the file drawer problem. So if we run 20 different studies and 10 of them don't work, we publish all the results together, put it all out there transparently. Even the 10 failed studies become part of the common knowledge, and that's really useful, I think. We can also do things that enhance interdisciplinarity. So if we can run tournament style field experiments like this, right? So you invite economists and psychologists and computer scientists, everybody can submit different ideas. They're tested in parallel, and you don't have the usual challenge of sort of how do you figure out how everybody can publish their results in different fields. So each study can be an island, and economists can publish here, psychologists there, but then you can publish the meta-analysis, essentially the mega experiment together. It also allows behavioral phenotyping, which is really what Edward was talking about. So trying to figure out what works best for whom, because you have a very wide set of treatments that you've tested. It provides a lot of opportunity for doing that kind of analysis. And finally, it just accelerates the pace of scientific discovery relative to the usual sort of one at a time process. I want to highlight that this is not a new idea to science by any means, but I do think it's a new idea in behavioral science. So a very similar idea revolutionized AI roughly a decade ago with, if you think about the common task framework, which is a model where researchers will, in AI or machine learning, will compete to solve the very same problem using the same constraints and the same data set. That's basically what we're doing here. So think about like image recognition. You might get the same corpus of images, and everybody's running their algorithm on that same corpus using the same validation method to see what wins. And there's total transparency in terms of tests and results. And so that's a really nice thing about this. It's very similar to that method. And then of course there have been scientific tournaments done before, which are similar in flavor, but they don't normally involve random assignment. So this is, I think, sort of pulling from other disciplines or other areas of science and trying to figure out how do we use the things that have worked well there in our field. Okay, so I'm going to tell you briefly about a model mega study in the time we have left, just to give you a sample of what I mean, not just give you the high level idea, but show you. So a mega study that we ran, the first one we ran was with 24-Hour Fitness, which is a 4 million member gym chain in the United States, a really big gym chain. And let me start by talking about the rationale and the goals. So you might be wondering, like, okay, if you're going to do a mega study, why don't we try to like end poverty or something like that? Why are you picking exercise? And I will admit that I think there probably are slightly more noble goals even we could have chosen for our first policy challenge. But it actually turns out that exercise is an important problem, maybe more important than a lot of people realize. So only half of Americans exercise sufficiently, and exercise seems to be like the closest thing we found to the fountain of youth. It's incredibly good for you for many, many reasons. It reduces risk of cancer, improves mental health, and so on. And actually 9% of premature global mortality is attributable to insufficient physical activity, which I found shocking when I learned. Even more importantly, honestly, to me, it's like the fruit fly of studying habits, because we can measure high frequency decisions objectively. And that's really hard to do in most contexts, right? We can't measure what people are eating. They have to tell us via self-report, but with the gym, you have to swipe in and out. So we have this objective measure of a repeated behavior, which is really attractive. So what did we test in this mega study focusing on boosting exercise? We had 30 different team scientists who all submitted ideas. They all designed experiments. They studied, or excuse me, they submitted 20 different pre-registered research studies. So each one was sort of an island, but then they're all tested simultaneously. And we had 53 different experimental treatments tested and one holdout control that I'll talk about in a minute. And what people who were in our project, all of the scientists, could vary was a few things. It was a light touch experiment. I think actually if we'd done something much heavier handed, it would have been easier to have a huge impact. You'll see the size of our results. I'm proud of them, but they're not, we didn't change, we didn't turn people who were lying on the couch at home into like marathon runners. So they could vary sign-up surveys. People sign up for this digital program, and they could vary the contents of that. So like I show you a video or something along those lines. They could vary the incentives they offered. They could vary the content of reminders sent to people to go to the gym, as well as send them interactive text messages and weekly emails for 28 days that were personalized. So that's what the scientists had to work with. And the most basic treatment that we tested compared to a holdout control sort of tried to build on best principles from existing behavioral science research. That was sort of, in a sense, a second control set. And that included prompting people to make plans about when they'd exercise, reminding them 30 minutes before every scheduled workout to do so, and giving them micro incentives for gym visits, about 20 cents per gym visit. And that was based on past work suggesting all those things might add some value. And then we tested, I don't expect you to read all of this. We tested a lot of different things, a lot of different ideas. Psychologists, economists, computer scientists all designed different treatments. And I'll just highlight a few big winners in a minute. Okay, so let me get to the methods. The study recruitment involved inviting all 24-hour fitness members to register for our program designed by scientists to create exercise habits. And they went to a website to do that. And we had 63,000 people roughly participate in the end who, skewed a little bit female, a little bit more from California than the rest of the country, and had been gym members for longer than you might ideally want if you're trying to, get people from the couch to the marathon running zone, but decently representative for a field experiment. And when people went to this website, they saw, and we assume most of them did it on their mobile phones, maybe when they visited the gym, they saw a landing page that looked very much like a professional program they're signing up for. They consent to be in our study, accept the terms, give us the contact info that we validate so we know we can really text them, and they're off and running. Then we randomize them to experimental conditions. So the holdout control group actually at this point is just told congratulations for entering our program, good luck to you essentially. And they're told that at the end of the program, they will be paid a small amount of money, about $1.20, which was equal to the amount we expected people to earn in other conditions that had incentives on average. So we're trying to hold sort of that gift exchange idea constant, but everyone's paid at the very end. So that's all that happens. If you're in the holdout control group, you're welcomed after you sign up. You're told you're going to get some money at the very end, and then you don't hear from us again. Compare that with our other treatment groups. So this is what happens to pretty much everyone in a treatment group. They're told they're going to earn repeated rewards. Welcome, you've earned some money, and here's the conversion rate, and you're going to earn more money every time you work out. And people could vary exactly how those incentives worked. They made a plan for the dates and times they would exercise. Additional A/B test content was inserted here. Maybe they had a survey, they had you watch a video, and then finally you're told, congrats, you're all set, and that's the end of registration. After that, they receive these reminders. Most people in most conditions receive reminders 30 minutes before they exercise. Again, not the holdout control, but other groups, and some kind of reinforcement of whatever the treatment condition is. So text message reinforcement a couple times a week, as well as emails reinforcing the message. Okay, so what happened? So I'm just going to sort of share some of the high level results. First, I'm showing you the control group. This is the placebo control group where basically nothing happened to them. You can see maybe there's like a little burst of excitement about exercise that leads you to sign up for this program. So there's like a little uptick right before they sign up, and then that kind of dies off fast. So it's pretty flat, not much happening with the control condition. So this is essentially a difference in difference estimator strategy. So I'm just showing you compared to the control group and with person fixed effects, because we have pre-intervention data. We ran a big regression. We see how did all of these different treatments we tested compare to that control group. The control group is the 0 line that I'm pointing to. And every dot on the x-axis is just showing you an estimated treatment effect relative to that. I do not expect you to read all the 53 treatment conditions labels. That will make you dizzy. I really just want you to see the distribution here. And the key finding I want to highlight is that our placebo control group was outperformed directionally by every single treatment we designed save one, and statistically significantly by 45% of the treatments we designed at a p-value of 0.05, and you'd expect that to happen by chance for 2.5% of treatments. So clearly we're moving the needle in a substantial way with a lot of the things that folks came up with, which is really exciting. A second comparison that I do think is important to point out is our planning reminders and micro incentives treatment, which we sort of designed based on best practices and was in a way a secondary control group. It was harder to beat that because that actually performed quite well. So that outperformed the placebo control, and only 9% of treatments outperformed that at a p-value of 0.05. Again, 2.5% would be expected to. So it was much harder to outperform this sort of best practice, but a few things did stand out. So let me highlight, I'm going to just highlight a couple big winners, top performers that, Bonferroni corrected, whatever kind of, none of this is corrected, but you can do any kind of correction you want. In our paper, we put everything in a table, and anyway, so even if you Bonferroni correct the heck out of this, the things I'm going to highlight are big winners. So big winners, one thing that really worked is highlighting, offering people a bonus to return after they missed a visit to the gym. So if somebody goes on Tuesday and had planned to go on Wednesday and Thursday, but they miss Wednesday, they can get a very small added bonus, 9 cents, a whole 9 extra cents on top of the 20 cents you would normally get for going at your scheduled time if you come back on Thursday after your missed Wednesday visit. So it's not enough that you strategically miss Wednesday to get those 9 cents extra on Thursday, but enough that I think it's more of a salience manipulation, like don't miss 2 days in a row, that would be bad. This turned out to be really effective. So it increased gym visits by 27% during the program to have this sort of pull or tug, not to have a streak of missed days, which I think is really interesting. And so this is just I'm just showing you graphically. I showed you a point estimate from regression, but graphically, this is kind of what this looks like, or not exactly what this looks like, in fact. Another thing that worked really well was just paying people more for scheduled workouts, a lot more. So we tried, amping up the incentive. So no shock, economists know that bigger incentives work, and they did. If we paid people a lot more for scheduled workouts, then they were more likely to go than if we paid them only 20 cents. And then a final, and this is just showing the effect size there, although that wasn't as effective as the 9 cents to come back, which is amazing. A final thing worth highlighting that was a big winner and was designed by Bob Cialdini, who is part of our team, and and who has done really important pioneering work on social norms, was reinforcing a rising social norm. So we told some people, truthfully, based on real data, that has been collected, that Americans are exercising more than ever before. The majority of Americans are exercising, and the numbers are up. And if you cut the data appropriately, everything we say is totally true. And that message that everybody's doing it, it's growing, increased gym visits a lot as well. And you can see that here. Okay, so I just wanted to highlight 3 big winners. I want to talk briefly about prediction accuracy, then wrap up because I know I'm close to time. So one thing we were wondering is, could people predict what we found in advance? If everybody could look at these 53 treatments and say, I know what the winners are, then you don't really need to do the mega experiment. You just pick the winner and run that test, right? So if we know in advance what's going to win, we don't need mega studies. We can spend less money and do one experiment at a time. We had a lot of different populations try to predict the treatment effects. So predicted, the actual treatment effect is on the x-axis here, and the treatment effect people predicted pooled across several different samples is on the y-axis, and you can see the correlation is 0. We did this with M-Turkers. We did it with people who are professors at public health schools studying exercise. We did it with behavioral science practitioners. Actually, the best performing group was M-Turkers, but they still didn't, they were 0.07, marginally significant predictive power. And the scientists on our team were also asked to predict the likelihood their own treatments would work, and had no ability to do that either. So we're really bad at predicting what will work. I do think it's worth saying this was a select sample. So we didn't launch anything that we didn't think had a really good chance. So it's not people can't tell complete garbage from great ideas. But once we filtered out the things that we said, these are brilliant behavioral scientists, and we looked at it, we think it's going to work, then there was no predictive power. Okay, so let me conclude. My key takeaways here. First of all, really exciting that 45% of our treatments significantly boosted gym visits by 9 to 27% at really low marginal cost on average, about 75 cents a person for the 4 weeks in our trial period. So I was really excited to see how well behavioral science did in the end, and only 2.5% would be expected to by random chance. But we were really bad at predicting what would work ex ante, suggesting these mega studies are valuable. And I think mega studies have a really exciting future for accelerating scientific discovery, comparing apples to apples, reducing risks and risk and fixed costs, and making it easier for interdisciplinary collaboration to happen. Really brief, infomercial, really, really brief. I'm really excited about work we're doing this fall to extend this method to try to figure out how we encourage people to vaccinate. Really important problem for COVID-19. And we actually had the opportunity to do tests around flu season with hundreds of thousands of people who had gotten a flu shot from Walmart pharmacy last year, or had a healthy visit with one of 2 large healthcare providers, Penn Medicine or Geisinger, and those study results should be rolling in the next month or so. We're really excited about what we'll be able to learn from testing dozens of different messaging techniques to try to encourage vaccination. Hope we'll be able to pivot and use that to help encourage people to get a COVID vaccine when a safe and effective one is made available. So let me stop there, and thank you all for listening.
Thanks a lot. Thanks for sharing this really, really interesting experiment. So I think we'll ask some questions more generally of all the speakers in a minute, but I just wanted to follow up quickly about this idea of people being able to predict these effects. And I guess, in some cases, we've seen that be successful with these prediction markets for replication, for example. And so what maybe was different here? Was it because a lot of these things were not necessarily replications? I also noticed that it seemed like a lot of the predictions were biased upwards. People were just predicting much larger effect sizes overall. So even setting aside the lack of correlation, it seems like somehow the predictions were just completely on the wrong scale for the treatment effects as well. So
I'm glad you pointed that out. That's a really important finding, and I should have noted that. So first, let me just double click on that. That was a really, really interesting thing we saw. People were much more overly optimistic, though, in the naive population. So M-Turkers, for instance, actually public health professors were, if I remember correctly, more biased. And then my recollection is that people working in applied behavioral science were less overly optimistic. They were a bit better but calibrated, but everyone was wildly overly optimistic. I do think part of that is there's a large literature on nudging gym attendance, and normally it uses much bigger incentives. And so I think they maybe were anchoring on the effects you get if you pay. For instance, Charnason and Easy did this wonderful study in 2009 in Econometrica where they paid people $175 for visiting the gym 8 times. And then they had these huge effects. And so maybe if we look at that graph and remember it, if you're an expert, you're like, oh, we're going to get huge effects, but we paid people 20 cents for visiting the gym. So really different scale in that sense. Okay, so the over-optimistic thing, I don't have a great answer, but I think it's really interesting, and that's my best guess, is just that we were using a much lighter tool, and maybe people anchored on past research that had used a hammer when we used a feather. The second thing I'll say about calibration, I mentioned this in my talk a little bit, but I do think it's really important that these were actually a lot of the tests were of new ideas, but they were all ideas that sounded really compelling. You know, we got brilliant folks to design them. The people on our team are superstars, and they're very good. You know, they looked and sounded all like good ideas, and then I think sorting between those is harder. I'm thinking of I was a participant. I remember when Devin Pope and Stefano Della Vigna did this wonderful prediction study on incentives. Like if you're an M-Turker and you're getting exposed to different incentives, like how many times will you hit the letter H or something, or the space bar? And that was a little easier because basically they were asking us to think about past research that we were familiar with and whether it would, what would happen there. And this is different. It's outside that range. Everything sounded good. It had all been filtered. So I think we had a pretty select sample, but I don't think that's unrealistic, right? Like if you are a policymaker and you have smart advisors giving you some suggestions for things that all sound good, you might be in a similar situation to the one we found ourselves in here. So I do think that's relevant. And you still have to pick the very best of a good set.
Yeah. Yeah, I think this notion of selection seems really important, right? Like in some settings when it's maybe, once you've paid these fixed costs or you're at a firm and just doing email experiments, if somebody has an idea, you might as well try it out. And so perhaps in that setting, predictions are somewhat better, though I think by and large, we see that actually people don't do a very good job even in those settings, right? That's why, some people have been, questing to, vanquish the hippo so much, is like just that, that people's opinions are often wrong about that. So actually on that point, and speaking of somebody questing to vanquish the hippo, Ronnie Kohavi was asking a question I think is relevant both to your talk and to Brett's as well, which was just this idea of how well some of these approaches work when we're trying sort of radically new things versus things that are more familiar. And so I think you kind of already commented on that, Katy, but he was asking like, okay, what's going to go wrong here, Brett, in this sort of proxy-based approach when people start trying something new? If you try a very different sort of advertising campaign, or maybe one that is an advertising campaign that includes promotions and you haven't been including promotional discounts previously, is this all going to fall apart?
Yeah, I mean, I think we require some notion of stability or stationarity or comparability. There's kind of a variety of ways of saying the same basic assumption. But if you take our basic this basic predictive model, it has a set of x's. It assumes a certain kind of relationship between the x's and the outcome. If you give it a new observation that is totally different, doesn't the x's don't lie within the range spanned by the original x's, or the relationship is somehow fundamentally different. Like what we're kind of relying on is that some notion of the bias between these metrics and the outcome is stable. Whatever that bias is, it's somehow stable. And if you test something where that isn't true, then it's probably not going to be a good prediction. But that seems like the best you can hope for. If you have a set of experiments versus you don't. If you don't have the experiments to begin with, you can't get any prediction other than the hippo, maybe. So.
And I wonder if there's an opportunity for some of the approaches you take to warn you when you somehow something's changed, right? And I mean, I could imagine even taking an anomaly detection approach here. If somebody says, hey, the experiments that you're running now don't look like the experiments you used to be running, it kind of seems like we're really extrapolating here. And so with some of these advertiser or experiment characteristics, I wonder if there's something you can do there, or whether when you're getting these predictions, some of the time you have much more precise predictions about the RCT effect than others.
Yeah, I think that seems possible. I mean, it seems like for any given value, if in the case, if you think that the uncertainty is kind of, or the unexplained variance is more due to the advertiser RCT characteristics than the metrics that we're using, then you could say, well, where do you have more data? Do you have many firms who are retailers, who are small, who are selling you items, and therefore you have a lot of data there to make a decent prediction, you think? Or are you looking at a type of experiment, a type of campaign where you only have 5 campaigns in your database, and then therefore the variance of your prediction is obviously going to be much greater? I think we could do something like that, but I think I think we'd love to tease apart when the metrics do better or worse. This is sort of to your question a while ago, and I think we have some limited tuition on it, but nothing definitive yet. It's on our very long to-do list.
Yeah. And just another question that came up related to your talk, and I think also maybe just more generally is relevant here, is just the prevalence of very small or null effects. I mean, that's sort of one of the patterns in your results, Katie, as well, is and also a lot of what you were presenting. The starting point, Ed, was, hey, the results on average are kind of null here. And I think especially, Katie, if you think of this best practice as your baseline, obviously then a lot of things were null compared with that. And so how should we think about some of these approaches in that context of sort of where there's very small effects? And so Brett, more particularly, you were looking at this mean absolute percentage error. And is that kind of the right measure to be using when we're talking about small versus large effects? And if our goal was mainly to distinguish small or null effects from large effects, do we do better there or worse?
I mean, I have thoughts on that, but I want to make sure I'm also not dominating the Q&A. So because this topic you said was also relevant to others. So if Ed or Katie want to, or Katie, I think
they're
okay.
telling you to go ahead. It looks like.
Okay, sure. The topic of the right error metric is one that we've actually spent a lot of time thinking about and really being very frustrated over. And I think one important kind of point to realize is that in a way, the right error metric here between the RCT and the non-experimental estimate is whatever the advertiser would care about. So if the RCT effect says you have a 1% lift and the model says it's 5%, some advertisers might say, great, 1.5, fine, whatever, that's practically the same for us. Whereas another one might say, oh, that's a 400% overestimate, that's terrible. So of course, in one case, you're arguing for a relative evaluation. In the other case, you're arguing for an absolute evaluation. And because we have such range, and I didn't get to show everyone this, but we have such range in the RCT estimates, some that are very small, of course, 30% of them are null at the 95% level, 5% level, 70% are not, but some are huge. It's very hard to kind of manage that variation in some kind of reasonable way with a metric and make it kind of easy to show in graphs. We've also looked at other metrics. It looks relatively similar. If anyone else has an idea for how we should handle this, we're totally open to it. So
yeah, and I think one of the challenges is, despite what you might think, Facebook doesn't always have all the data, right? And that in this case, the advertisers are making decisions based on things like what they know about their margins and what a conversion actually corresponds to in terms of profits, et cetera. And you don't have that data when you're analyzing these experiments, so you don't know whether at what cutoff are they going from positive ROI to negative ROI, and so that's I think that's challenging as well. One question, and feel free to chime in on that as well, Ed or Katie. But one question kind of directed to you, Ed, about about doing this anomaly detection approach. Have you done this with many experiments? I mean, that sort of seems like one of the things that's prompted by this, or would I say many treatments? I mean, the example you talked about from the STAR experiment, you focused on a treatment control contrast. And what happens if we try to scale this up to a mega study? What does that look like?
That's a really good question. And actually, so the paper that I referred to, the working paper I referred to about the with propensity score reweighting is actually addressing that question a little bit as well. So specifically, that context, it's a medical study. It's in medicine. Basically, we have a bunch of data from doctors and from insurance companies with EHR data, basically. And the idea is that, you know, if you go to a hospital, if Dean goes to a hospital in Cambridge with the same ailment, a doctor may give him one thing, whereas if he goes to one in Minneapolis, a doctor may give him something else, right? For the same exact person, same exact treatment. And so because we obviously doctors, we don't get randomized people to doctors, we can't make it an RCT, but you can imagine that trying to at least some sense get a sense of controlling for the observable the doctors could have seen and adjusting for that. And what we're doing there is trying to match subpopulations to treatments, to treatments basically. So the idea is that maybe we found this in the actual paper that, for example, glucocorticoids is actually could lead to larger amounts of time spent in the hospital with certain comorbidities than it would other subpopulations for older men. And there's apparently a debate, and not a doctors, but the debate going on in the literature about the effectiveness of glucocorticoids for heart disease, right? So like these things are happening apparently, and I don't even know, but we show it to, you know, our collaborators, and they say, oh yeah, this actually is an interesting thing. We're trying to figure this problem out now. Like we're having this debate in the literature right now about the effectiveness. So there are ways to scale it up. And again, especially when you go outside of the context of randomized experiment, it's very clear that we should be saying we are trying to generate ideas or hypotheses, not claim that this is exactly the final truth. But hopefully we shine a light on it. People like Katy and Brett can then run experiments to actually really test these ideas out effectively in mega studies or sort of across many experiments and really make sure that they're actually, you know, plausible. You can imagine this happening with COVID testing as well, right? This thing where we see effects overall, 95%, you know, effectiveness for the vaccine, but potentially the vaccine's not helpful for everybody. Maybe some people it's not really effective for them, and we want to make sure we're not giving them the vaccine and then send them out in the wild to affect or be infected themselves. And those things are very important.
Yeah. And actually, just on that point, thinking about heterogeneous effects of these treatments, I think that's a natural question for you, Katy, is just what else are we seeing there in terms of heterogeneity? And I would think that's actually another benefit of this kind of mega study approach is that basically you have many of the exact same covariates at baseline, right? I mean, when you said, oh, there's this central person who pays all the fixed costs, it's basically like you and your team. And part of that is now also you have all these covariates available at baseline. And so you've created this environment that's not unlike the kind of environment Brett's working in, where you have so much, you know, the same common data framework. So what have you been looking at in terms of heterogeneous effects?
Yeah, great question. And we have an awesome machine learning team that is writing a paper right now on this very question, led by Rahul Ladhania, who's a professor at UMichigan. And yeah, and a friend of yours, Ed. I love that reaction. It's almost like we're in a room together saying, wow, it's so human. So Rahul is great, and he's leading our efforts on that. And I will say a couple things that we're looking at. First, one question that we found really interesting is actually to just compare the heterogeneity estimates you get if you do like what scientists usually do, which is have a few subgroups that you predict will outperform. So we actually asked all the scientists on our team to tell us, like, what slices would you do if you were just going to do heterogeneity the boring old way? Like, would you predict that women are going to outperform men and look at that? Would you look at age? So they gave us their sort of pre-registered anticipated slicing that they would do. And then we said, let's see how much better machine learning can do at understanding heterogeneity than that old-fashioned way of going at it, which is just like, I do some subgroup analyses. So not shockingly, obviously, we're seeing some evidence in the early data that machine learning is a lot better than our old-fashioned methods. And there is, the early results also suggest there are benefits to slicing and not just delivering the same treatment, the average best performer to everyone. But I'll leave it to you guys to invite Rahul to come maybe next year and talk about the full set of results. And we'll be doing the same thing with the data we're collecting right now on flu shots. And I actually expect that to be even more powerful. My guess is that the messaging around vaccination might be something where we'll see even more heterogeneity than what messaging works to get a person to go to the gym. And I think given what we know about the diverse populations and the diverse set of concerns they have about vaccination, that thinking about that problem is going to be really valuable.
Yeah, cool. Yeah, we're also working on vaccine acceptance, so it's really exciting to see that you're on that case. One final question, because we've sort of run over time into the break here, but kind of directed at you, Ed, is just comparing TESS to another approach like a causal forest, or even just a causal tree, and how we should think about the trade-offs there.
I think it's a great question. And actually in the full paper, in the full talk, I talk about this. I actually compare against both of those methods because they are kind of seen as maybe the standard in front of heterogeneity. And I would say two major things. One is that those methods, their objective is different. Their objective is to estimate the entire response surface very effectively. And if your job is to estimate the response for everybody, well, then they're going to probably be better. But if your job is to identify the subpopulation that is most affected, their optimization is not built for that. They're built for risk minimization, minimizing the predicted error in the treatment effect across the response surface. So that means you might use a lot of your power to be very sure the effect is zero in a certain subpopulation, which if your job is to try to target people, that's a waste of power. If your job is actually to, find the effect, the word's maximize, then you might use that information and power to focus on the group that has the largest effect, ignoring those who clearly have evidence of no effect. Even if you're not sure, but it looks pretty certain, don't waste your power on that. So that's the kind of the trade-off between, I think, methods like that and the one we're doing. And so if your job is to get that overall aspect, it makes sense to use those because that's what it's trying to do.
Yeah, and it seems like one of the big appeals of your approach can actually be finding really negative effects.
Yes.
Where it's these could be launch blocking kinds of effects if it's like, and it may inform you, especially in a lot of digital settings, oh, actually we never really tested that treatment fully on this platform.
Yes.
And so it turns out people with this version of iOS are having a tough time. And that can be really valuable information. Yeah.
We've been talking to a couple of digital platforms about that. And often what happens is that it's the last case where you run an experiment and you see an overall effect that's positive and you say, oh, great, like we succeeded. But in reality, there might be some small group of your population who is really adversely affected by it. And they get washed away by all the other null effects or positive effects. And so they're getting further and further damaged in some way, and you have no idea. And so the ability to know that, so that when you roll these things out, you're not inefficiently providing this treatment, is very powerful. It's just knowledge, again, like knowing these things and discovering these things and kind of having a way to have that presented to you, I think is very powerful for understanding. So I think that there's value in it, certainly.
Cool. And so we're at time or past time. So I'm gonna go ahead and conclude this panel discussion. I think there was some more interesting questions in the Q&A for all of you, but I encourage all our participants to head back into Gather, or if you're presenting in the next parallel session, to head, to make a beeline towards your parallel session so that you can test your slides and make sure we're all ready to go at 11:15 with the parallel session. So thanks a lot, Brett, Katie, and Ed. This was really interesting. Thanks a lot.